In this lesson, I cover watchdogs. Watchdogs are a key tool to ensure your embedded application is healthy. And if your application isn't healthy, a watchdog will trigger recovery action. This can be important for safety or for availability. So here's an outline of this lesson. I start with an introduction, then a small set of requirements for a watchdog module. Then I discuss the design of the module at a high level. I go over the module API and then its implementation in C. I give a small demo of the Watchdog module. Then I go over some prompts or questions and my take on them. And I finish with a summary. So a watchdog, which is sometimes called a watchdog timer, is a software or hardware mechanism used to detect faults in a software system. Generally, they detect something isn't being done. Maybe something is stuck. So the software must periodically feed the watchdog to tell it that it's alive and well, everything's fine. If the software goes too long without feeding the watchdog will trigger, and this means something is going wrong in the system. When a software-based watchdog triggers, we can take some software-based action. For example, this could include saving information about the state of the system when the watchdog triggered, or some kind of controlled shutdown of the system. In this course, we will be implementing a feature where information is saved. Now, if a hardware-based watchdog trigger, it generally just does an immediate hardware reset of the MCU. It's like boom, reset. However, some hardware-based watchdogs do have the ability to issue an early warning interrupt before the reset. So in other words, when it gets close to triggering, it first will issue an interrupt to give the software a chance to quickly do something, and then a short time later it will reset the MCU. Some STM32 MCUs have this feature, but the one we're using doesn't. So different STM32 MCUs have hardware-based watchdogs with different features. And this is beyond the early warning interrupt I just mentioned. So one feature is the type of clock that drives the watchdog. Generally, there is a trade-off between the accuracy of the clock and the reliability of the clock. This is mainly a hardware issue, and the details are beyond the scope of this course. Another feature is whether you have a simple timeout or a windowed timeout. A simple timeout means you just have to feed the watchdog before the time expires, and this is what I've been discussing so far. A windowed timeout is where the software must feed the watchdog precisely within a specified time window. It can't feed it too early, and it can't feed it too late. So far, I've been talking about a system that is in steady state, doing its thing. But I want to bring up system initialization just for a moment. Initialization tends to be a lot different than steady state operation. And of course, a system can get stuck in initialization before most of the infrastructure is set up and running. What this means is that initialization might be handled differently in its own special way compared to steady state when we're talking about watchdogs. And I'll talk about that later in this lesson. So finally, I want to talk about watchdog usage strategy. This is just based on my experiences and what I have done on projects. So the idea is to have multiple, perhaps many watchdogs. And these will have to be software-based because most MCUs support at most one or two hardware-based watchdogs. Then each of those watchdogs ensures that some piece or pieces of critical work is being performed. So for example, perhaps the system has to read its inputs every 100 milliseconds. So you have a watchdog for reading inputs, and you only feed it when you have successfully read the inputs. Perhaps there's another watchdog for ensuring the control loop has successfully created and written an output value. So the idea is watchdogs do more than ensure that some branch of code, for example, the main loop, is being executed. The main loop could be running fine, but the product isn't doing its job because there's some data that is in a bad state. Now, you might have a watchdog on the main loop. That's okay and maybe a good idea, but I'd argue you need more than this. Now, with this strategy, the usually single hardware-based watchdog is used to ensure that the software-based watchdogs are being processed correctly. So it checks the checkers in a kind of hierarchy. And so, in summary, I want to emphasize this key principle. Watchdogs are to ensure that critical work is being done, not simply that code is being executed. For my embedded courses, I use an architecture based on a super loop and modules. So naturally, I have a Watchdog module to provide that functionality. And here's a list of the basic requirements for that module. First, it needs to support multiple independent software-based watchdogs for monitoring different parts of the system. This is based on the watchdog usage strategy I just went over. Next, software-based watchdogs are established at runtime using a registration technique. There are not codependencies between the watchdog module and modules that use watchdogs. There is support for a single module that can register to get notification of a software-based watchdog trigger. So later we'll see a fault module that handles the watchdog trigger event. Now the hardware-based watchdog should only be used as a backup when the software-based watchdogs are not working correctly. We need to support a single simple watchdog for initialization. In other words, the system has some limited amount of time to finish initialization. Now, with some products, you don't want it stuck in an initialization loop forever. So there is a requirement that after n consecutive failed initialization timeouts, don't enable the watchdog. Just let it go. Now, you can set n to infinity if you want to keep trying forever. Now, after this, there are common requirements for all modules. One is requirements for the superloop environment. It needs to use a standard API, and of course, all functions must be non-blocking in a superloop design. And then finally, there are common requirements for test and debug. This means that the module must do logging, for example, when errors occur, and there must be console commands to dump state information and test operation. So here's a conceptual view of how the Watchdog module works. On the left, we have these green ovals that represent application software that is performing critical work. For each one of these ovals, we have an associated software watchdog, and the application software will be feeding this watchdog if it successfully does its work. Now, this set of software watchdogs is periodically checked, say every 100 milliseconds, to verify that none have triggered. In the normal case, where all of these software watchdogs are okay, the hardware watchdog will be fed. So everyone is happy, everything's working. So now let's look at a normal watchdog fault. So let's say this application software is having a problem, and so it stops feeding its watchdog. So this will be detected when the software watchdogs are checked periodically. So when this triggers, the watchdog module will notify the fault module, and we expect the fault module will save some information, and eventually it will reset the MCU, and hopefully the system starts working again. So that's a normal watchdog fault. Now let's look at some more interesting failure scenarios. As the first failure scenario, let's say this periodic checking of the software watchdog stops happening for some reason. Something got messed up. This is a serious problem because our watchdogs are no longer being checked. But if that happens, then we never reach this condition where we determine that all the software watchdogs are okay. It means we stop feeding the hardware watchdog, and it will eventually reset the MCU because the watchdog system went bad. And again, we hope that the system restarts and everything starts working fine again. As another scenario, assume, let's say this software has a problem. It stops feeding its software watchdog, and this software watchdog triggers, and again, the watchdog module notifies the fault module. But let's say the fault module, when it's doing its thing, it gets stuck. We don't want to stay stuck forever. But here's what happens. When it's stuck, no one is feeding this hardware watchdog because we have stopped scanning these software-based watchdogs. And so eventually the hardware-based watchdog will reset the MCU. And again, we hope it recovers. So this is a system of checks. I hope I've covered all of the use cases, and hopefully we have a simple and reliable design. I want to say a few words about the initialization watchdog design because there was one part of it that was a little tricky. So as I mentioned, the hardware-based watchdog by itself is used for initialization, for the case where initialization gets stuck. Now we have a requirement to stop using the watchdog after n consecutive failed initializations. This is a last-ditch effort to get the system to come up and maybe help someone figure out what's going on. So a way is needed to count failed initializations across MCU resets. Now this is tricky because normal, global, and static variables are initialized after an MCU reset. These are in the .data and .bss sections for those of you familiar with these concepts. I cover that in my introductory course on embedded, and we see how these areas are initialized in the startup code. So a no-init-var memory block in RAM was added to the linker script, and we'll look at that in just a moment. This block does not get initialized after the MCU resets like normal global variables would. So this memory block contains a consecutive failed initializations counter used to decide whether to start the hardware watchdog at the start of initialization. So this counter counts as initializations failed consecutively, but it is set to 0 when one of these events occur. One is a successful initialization occurs, obviously, and another is if the memory block contains invalid information. That would happen, for example, after a power cycle when all RAM is lost. So we start, if we go through a power cycle, something happened and we'll start from 0. And then the last thing is if the previous MCU reset was not due to a hardware-based watchdog. We're trying to limit consecutive failures when the system is resetting itself. If someone pushes the reset button, for example, we start over. So by the way, another choice would have been to store this counter in Flash. Then it would in some ways make things easier, but writing to Flash has its own issues, and so I chose this method as being a little bit simpler. So here we are in the linker script file, which is in the project workspace, and in my case the file name is stm32f401 retx_flash.ld. So this file is used as part of the build process, and it basically tells the linker how to assign code and data to Flash and RAM, and ultimately assign addresses. I described this file and how it's used in my introductory course on embedded. So I'm using a IDE, the STM32Cube IDE, and it actually generates this file. So for simple projects, you never really need to worry about it. But here we're doing something out of the ordinary. So let me go to the changes I made here, which are on line 163. So I added these lines. So the first line is just a comment saying what this purpose is. And then I'm not going to get into the syntax here. It's not critical. The point to remember is we're defining a new section of memory. And this line here in particular is telling it to put variables that belong to the .no, .init, .vars section into this area of memory. And this is saying that this area of memory is in RAM. The other thing we can tell by looking at the position of these lines relative to other definitions, we can see where it's going to go. And right before it is the .bss section. So it goes right after .bss and right before the user heap. So we'll see shortly how you tell the compiler that you want a variable to go into this section. And again, the whole purpose of this is these variables that are in here will not be touched by the startup code after reset. So now let's look at the API of the Watchdog module. Keep in mind this module can be thought of as providing a Watchdog service to other software. and that other software is normally inside other modules. So we're in the header file. First thing, here is a type def for a function pointer, which is the callback function that the Watchdog module calls when a Watchdog has triggered. And I like to use type defs when using function pointers just because the syntax is always a little confusing. These first two APIs are just part of the standard APIs for a module, so I won't talk about those. Then these are the Watchdog specific APIs. This first one is used to register a Watchdog, where the client software passes in the Watchdog ID. These are defined statically, and they're in config.h, and then here's the period for the Watchdog in milliseconds. This is the way to feed a Watchdog to keep it from triggering. It's pretty straightforward. This is a method or a function to allow, in our case, the fault module to register a callback to say, call this function whenever a Watchdog triggers. These next three APIs regard the hardware Watchdog. And this first one is to start the hardware Watchdog for initialization. Now, based on that logic of preventing endless initializations, this function may or may not actually start the hardware Watchdog. This API is telling the module that initialization succeeded. The module needs to know that based on that logic to prevent infinite looping of hardware initializations. And then finally, this function here does the actual work of initializing the hardware Watchdog. And it's the one that's also used when we enter steady state. So now let's look at some selected code in the implementation file. First, we'd like to look at some data structures. Here is the structure for a soft Watchdog, which just contains the Watchdog period, and then the last time it was fed, which is a timestamp in milliseconds. This is the state data for the module, which is just an array of software Watchdogs, and then the callback pointer, the function callback pointer used if a Watchdog triggers. And then finally, here is the no initialization variables structure. We talked about this before. And the main thing in here is this consecutive failed initialization counter. Now there's two other variables in here, magic and check, and these are used to basically verify whether the data block is valid or not. For example, after a power cycle, it wouldn't be valid. So the next thing I would like to look at, 121, is the Watchdog, the no init vars. Here's where we actually declare a variable, and we'll call it no init vars. It's of that structure. And then here is the key information. This underscore attribute keyword is not standard C, but it's supported by the GCC compiler, and it allows you to tell the compiler what section this variable should be in. And here we tell it. This information then gets passed to the linker, and then the linker uses this when assigning variables to memory. And if you remember in the linker script, we told it where it should put variables from this section. So that takes care of the no init variables. So let's go start looking at some code. This is the standard start function for this module. And the key thing in here is we are starting a timer. And this timer is the one that will actually be checking the software Watchdog timers. And this tells how often the timer is going to run, and that's 10 milliseconds. Of course, it's tunable. So here is the client registration when a client wants a Watchdog, and it passes in the Watchdog ID. These are static values which are assigned at compile time. They're in config.h, and here's how long the Watchdog should be. And this is pretty straightforward. It's just filling out a data structure. So let's look at the feed API. That's really simple. All it does is that last feed time in milliseconds, it updates that to the current timestamp. So next, this is the function that starts the hardware watchdog timer at the beginning of initialization. It either starts it or it doesn't start it. It might not. And the first thing it does, first of all, it validates the no init vars. And what this function does is looks at that data structure and validates whether it's correct or not. If it's not correct, it reinitializes it. So the first thing we do is look to see whether the reset that has just occurred was due to the watchdog timer. If it wasn't due to the watchdog timer, something else happened, power cycle, button was pushed or whatever, and we set the consecutive failed initializations to 0. And then this is the logic that actually decides whether to start the watchdog, and based on that, it will either call this function, which actually starts the watchdog, or it won't. Notice we update the failed initialization counter. We assume it's going to fail, and if it does fail, we won't have a chance to increment that counter, so we do it here. But of course, if the initialization succeeds, we set that counter to 0. So here is the code that actually does the low-level details of starting that hardware watchdog timer. I won't go in this. It looks sort of complicated. I tried to make the calculations very clear, but what it's doing here is computing a count value based on the clock rate and other factors. And then right here is it's actually loading the registers of the watchdog timer. And you notice it uses the LL or low-level library to set those registers. I wanted to point these out. This is interesting. I found this out the hard way. By default, when you use a hardware watchdog timer and you're running in the debugger and you hit a breakpoint and the debugger stops running, or the code stops running, the hardware watchdog timer does not stop running. And what happens is you get a breakpoint, and then shortly thereafter, the MCU resets, and that makes it hard to debug code. These lines tell the MCU, we're setting some register values here, and it's telling it when the CPU stops, stop the watchdog as well. So the final thing I'd like to look at is that timer callback, and that is going to check the software watchdog timers, and that's exactly what it's doing in this loop. And right here, and here it's checking the timestamps and so forth, and here is the case where a watchdog has triggered, and it's calling the callback function, which in our system is going to go to the fault module. And then here is the very special code. If no watchdog triggered, this line here actually is reloads the hardware watchdog, and that's what we would call feeding the hardware watchdog. So there's more code here to look at, but I'll just stop here. So now I want to do a demo of the watchdog module. Now it's hard to do a demo of anything very interesting with this module on its own. We really have to get other modules involved, and so that's what I'll do. So first, I have a module called temp_hum for temperature humidity. I developed this module for my I²C course, and it communicates with a temperature humidity sensor. For this course, I added a watchdog timer to temp_hum that will trigger if it has problems getting measurements. So let's look at some key code. Here is some new code where it registers a watchdog and passes in the ID and the time and the period, which I think is 5 seconds. There's a hash if on this because this is sort of an optional feature for this module. So the other key line is 333. Here's where we feed the watchdog. And this code is in the middle of a big state machine. It goes through the module has to go through several steps to request and get a measurement and validate it and so forth. And if everything is good, then the watchdog will be fed. If it has any problem along the way, it won't get fed, and eventually the watchdog will trigger. So the other important module is the fault module, which is a new one for this course. It is the module that will be notified if any watchdog triggers. So in our demo of the watchdog module, we will see actions being taken by the fault module. And I'll explain this as we go. So let's get started. So here we are at the console. What you see here is the temp hum module logging its samples out to the screen. So I'm going to begin by resetting the board, and then I'm going to enter Control L, which is used to toggle logging on and off. So now it's off. And I just want to point out that when you reset the board, the first 3 lines that come out are these, and we'll be seeing those later. So I want to show the watchdog status command, and there's some information here. The key thing I want to point out is it has a line for each software watchdog, and there's only one for the temp hum module. But if I enter this command over and over, you can see these last 2 numbers change. And this is the last time that watchdog was fed, and this is how long it's been in milliseconds since it was fed. And you can see those values changing as we go. So now I want to cause this temp hum watchdog to trigger. And I can do that with a I2C test command. The details of this really aren't important, but what this is going to do is reserve the I2C bus that the temp hum module needs to operate, and that will cause problems, and it'll eventually cause its watchdog to trigger. So let's turn the tracing on, and now I'm going to enter that command, and now it has stopped taking samples. And let me stop this and we can look at what happened. So it stopped taking samples, and a few seconds later we get this output, and this is coming from the fault module, and it's saying I had a fault of type 1, that's a watchdog, and this is the watchdog ID, which is 0. We'll talk about this information in a later lesson. And then the next thing we see is those init lines. So the fault module had reset the MCU, and because the MCU got reset, that cleared out that reservation, and now the temp hum is working again. We sort of recovered, I guess you could say. So there's one more thing I want to do, and that is there are some watchdog test commands to test various things, and one of the things I can do is prevent the watchdog module from feeding the hardware watchdog. And if you look at the code, you'll see there's a flag in there that does this. It's very simple. So this is the name of the command. I'm just going to copy that into my paste buffer, and then I'm going to turn logging back on. So I'll enter the command. Now it continues taking measurements, but there it goes. The system just reset. So what happened is we stopped feeding the hardware watchdog. It then reset the system right here, and then we start up again. And you'll notice in this case the fault module didn't get involved, and that's because it didn't have a chance. The hardware watchdog expired, and it just directly reset the system. So that's it for the demo. I just want to add, I used small values for the watchdog timeout periods, like 5 seconds. This was to keep the demo short. In a real system, you sometimes pick much larger values than you think you need, just in case. The idea is you don't want to have systems resetting, and then later you look into it and you find out, oh, I set those watchdogs too low, and those resets weren't needed. So here are the prompts for this lesson. I'll just pause a second and then go through them. How might the watchdog module be enhanced to support the case where a client is going to be busy for a little while and won't be able to feed the watchdog during that time? I ask this because I think I had to do this on some project. I can't remember what exactly the circumstances were. So there are some options I thought of. One is to have a way to simply increase the timeout period on the fly. Uh, it would be up to the client to put the timeout period back to the original value when it's done. I think the thing I didn't like about this is this forces you as the designer of the software to be able to predict how much time you're going to need. And that might be difficult. Another one is to have an API just to tell the Watchdog module to stop checking this particular watchdog for a while. And then another API to say, okay, you can go start checking it again. And I think that's what I did. Another option is to use this timeout handler feature, which is actually part of the next prompt, where a client can intercept a watchdog trigger. How might the watchdog module be enhanced to support the case where a client might want to try to handle a trigger event itself before allowing the system to be reset? So the way I thought of doing this is to add a parameter, call it handler, to the registration API, where the client could specify a function to be called when the watchdog triggers. So if the watchdog triggers, then the watchdog module would use this callback function first, and then based on that function's callback function's return value, the watchdog module could either just ignore that the trigger ever happened, or it could pass it to the fault module as normal. So in other words, this would allow the client to say, oh, never mind, ignore that watchdog that just expired. I took care of it. So here's a short summary of the lesson. Watchdogs are a common way to ensure the system is performing its function. Hardware-based watchdogs, when supported, typically directly reset the MCU. But sometimes you want to take some actions before the system is reset. For example, saving state information that will help you figure out what happened. This can be accomplished with software-based watchdogs that trigger before the hardware-based watchdog, or at least under normal conditions. And some hardware watchdogs do support an early warning interrupt. That is another way of accomplishing that. So I hope this lesson was useful, and thanks for watching.